Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Within the grand edifice of late 19th century physics, an architecture of thought that seemed almost complete, Henri Poincaré stood as a figure of unique and penetrating insight. The year 1893 marks a pivotal moment, a fulcrum upon which his thinking turned from pure mathematics toward a profound philosophical interrogation of the very foundations of physical science. While he produced no single volume titled The Laws of Physics in that specific year, his lectures, papers, and intellectual trajectory coalesced around the central theme that would redefine the epistemological status of scientific knowledge. He began to articulate a philosophy of conventionalism, a subtle, powerful doctrine that questioned what a physical law truly is. Poincaré's work of this period was a response to a physics confident in its deterministic and mechanistic worldview, a universe conceived as a grand clockwork mechanism governed by the immutable laws laid down by Isaac Newton and refined by P.S. Simon Laplace. It was into this milieu of supreme confidence that Poincaré introduced a form of sophisticated, constructive doubt, born from his unparalleled mastery of both mathematics and physical theory. His critique was internal, using the very tools of classical mechanics to reveal its deep conceptual fissures. The genesis of Poincaré's thought lies in a confluence of 19th century intellectual currents. The dominant physical paradigm was Laplacian determinism, the belief that a complete knowledge of the positions and momenta of all particles in the universe at one instant would allow a supreme intellect to calculate the entire past and future. This view posited physical laws as direct, unmediated descriptions of reality. Simultaneously, the philosophical landscape was shaped by the legacy of Immanuel Kant, who argued that certain structures of thought, such as Euclidean geometry, were synthetic a priori intuitions, necessary preconditions for any experience of the world. Poincaré, deeply learned in philosophy, engaged directly with this Kantian inheritance. The critical catalyst for his new perspective, however, came from mathematics itself. The development of non-Euclidean geometries throughout the century by Nikolai Lobachevsky, Janos Bolyai, and Bernhard Riemann demonstrated that consistent, logical alternatives to the geometry of Euclid were possible. This mathematical revelation provided Poincaré with his master analogy. If one could construct logically sound worlds with different geometries, then the claim that our space is inherently Euclidean lost its status as a necessary truth. It became an empirical question, or, as Poincaré would brilliantly argue, something else entirely. The core of Poincaré's work around 1893 was the formulation of his doctrine of conventionalism. He argued that the foundational principles of a science, particularly the axioms of geometry and the general principles of mechanics, are conventions. They are definitions in disguise. They are selected by the scientific community on the grounds of convenience, fruitfulness, and simplicity. They are what he termed disguised definitions. The classic illustration he repeatedly employed was the status of Euclidean geometry. He posed the question: if we were to conduct a parallax experiment on a very large triangle and found the sum of its angles to be something other than 180 degrees, would we conclude that space is non-Euclidean? Poincaré's answer was a resounding no. He argued that we would have a choice. We could abandon Euclidean geometry and adopt a non-Euclidean framework to describe the world. Alternatively, we could preserve Euclidean geometry and instead postulate the existence of a new, unobserved force that bends the path of light, causing our measurements to deviate. The choice between these two descriptions, one with simple physics in a complex geometry and the other with complex physics in a simple geometry, is a matter of convention. There is no experiment that could compel us to choose one over the other. We choose Euclidean geometry because its simplicity and our long familiarity with it make it the most convenient language for describing the physical world. These conventions are what he called indifferent to experience. They are the linguistic and conceptual frameworks we create, and while they can be replaced if they become too cumbersome, they can never be falsified in the way a specific empirical hypothesis can. This was a radical departure from the prevailing view of physical laws as direct reflections of reality. The law of inertia, for instance, is in this view a convention, a baseline definition against which we measure what we call force. It is unfalsifiable because any deviation from uniform motion is, by definition, attributed to the action of a force. This philosophical posture was deeply intertwined with Poincaré's concrete mathematical research, most notably his monumental work on the three-body problem. In his 1889 prize-winning memoir for King Oscar II of Sweden, he had sought to prove the stability of the solar system. What he discovered was something far more profound and unsettling. For the classical worldview, he demonstrated that for a system of three bodies interacting under Newtonian gravitation, the equations of motion, although perfectly deterministic, could exhibit solutions of immense complexity. He showed the existence of what are now called homoclinic tangles, where the stable and unstable manifolds of a solution can intersect infinitely many times. The implication was staggering. An arbitrarily small change in the initial conditions of the system could lead to enormous, qualitatively different outcomes over time. This phenomenon, now known as sensitive dependence on initial conditions, is the hallmark of deterministic chaos. Poincaré had uncovered a fundamental unpredictability lurking within the heart of Newton's supposedly clockwork universe. Even for Laplace's hypothetical demon, armed with perfect knowledge of the laws, a minuscule imprecision in measuring the initial state would render long-term prediction impossible. This mathematical discovery provided a powerful physical motivation for his philosophical skepticism. If the deterministic laws themselves could generate behavior that was practically indeterminable, it reinforced his view that our laws are useful, simplified models, frameworks of convenience, whose claim to absolute truth is deeply problematic. The search for a general, close-formed solution, a formula that could describe the system's evolution for all time, was something he proved impossible. The system's behavior was a testament to a complexity that simple algebraic expressions could fail to capture. The immediate reception of Poincaré's conventionalism was complex. Among many practicing physicists, who were deeply invested in the realist project of uncovering the true nature of the universe, his ideas were met with a degree of suspicion. They seemed to open the door to a radical relativism, suggesting that scientific truth was a matter of mere taste or communal agreement. His contemporary, the physicist and philosopher Pierre Duhem, was developing a related but distinct thesis. Duhem argued for a form of holism, stating that an experiment never tests a single hypothesis in isolation but always an entire web of theoretical commitments. While this shares a family resemblance with Poincaré's thought, their emphasis is different. Duhem's holism is a methodological problem concerning falsification, whereas Poincaré's conventionalism is a deeper epistemological claim about the definitional status of certain principles. To counter simplistic interpretations of his work as pure instrumentalism, Poincaré clarified his position in later writings. He was a conventionalist about the general framework principles, yet he remained a realist about the relations those principles helped to express. He believed that while terms like ether or force might be convenient fictions, the mathematical equations that related them expressed real, objective relationships within the world. Science, for Poincaré, did progress. It did so by discovering ever more encompassing and accurate structural relations, even if the ontological status of the theoretical entities themselves remained conventional. This position is now often referred to as structural realism, and Poincaré stands as one of its earliest and most sophisticated proponents. The most profound and historically significant application of Poincaré's philosophy was its direct influence on the development of relativity. Albert Einstein's creation of the special and general theories of relativity stands as a vindication of the Poincaréan mode of thought. Poincaré himself had come remarkably close to formulating special theory. By 1904, he had articulated a comprehensive principle of relativity, explored the mathematical properties of the Lorentz transformations, which he named after Hendrik Lorentz, and understood that these transformations form a mathematical group. He had even proposed that the synchronization of distant clocks using light signals was a key procedure, implicitly recognizing the relativity of simultaneity. His physical interpretation, however, remained tied to the concept of a luminiferous ether, even if this ether was, by his own principle, fundamentally undetectable. He saw the Lorentz transformations as the peculiar mathematical description of how objects contract and clocks slowed down when moving through this undetectable medium. Einstein's breakthrough in 1905 was to make a quintessentially Poincaréan move, albeit with a boldness that went beyond Poincaré's own conservative instincts. Einstein took the principle of relativity and the constancy of the speed of light as his two postulates. From these, he derived the Lorentz transformations as a description of the very structure of spacetime itself. There was no need for an ether. The relativity of space and time was a direct consequence of the postulates. This was a choice for conceptual simplicity and elegance. Later, with the general theory of relativity, the influence became even more explicit. Faced with the challenge of incorporating gravity into this new relativistic framework, Einstein realized that the laws of physics could be made much simpler and more universal, or covariant, if he abandoned the assumption of a flat, Euclidean spacetime. Instead, he adopted the non-Euclidean geometry of a pseudo-Riemannian manifold, where the curvature of spacetime is determined by the distribution of mass and energy. This decision was a textbook example of Poincaré's conventionalism in action. Einstein chose to change the geometry of the world in order to preserve the simplicity and covariance of his physical laws of gravitation, as encapsulated in your Einstein field equations, which relate the Ricci curvature tensor, the scalar curvature, and the metric tensor to the stress-energy tensor. He changed the stage to simplify the play. Einstein himself acknowledged Poincaré's foundational role, recognizing that the French polymath had sharpened the conceptual tools that made the revolution possible. The later evolution of Poincaré's ideas saw them absorbed and transformed by subsequent philosophical movements. The logical positivists of the Vienna Circle in the 1920s and 30s, particularly Moritz Schlick and Rudolf Carnap, were deeply influenced by his conventionalism. They adopted his view that the axioms of geometry were definitions and that scientific language played a crucial role in structuring our knowledge. They, however, integrated this insight into their broader verificationist program, developing a sharper distinction between analytic statements, true by definition, and synthetic statements, verifiable by experience. They arguably lost some of the subtlety of Poincaré's original formulation, which saw conventions as being motivated and constrained, though determined, by empirical considerations of simplicity and fruitfulness. His work continues to resonate in modern philosophy of science, particularly in discussions surrounding the underdetermination of theory by evidence, which asserts that for any finite body of data, there will always be an infinite number of theories that can account for it. Poincaré's conventionalism provides a powerful framework for understanding how scientists make choices in such underdetermined situations, appealing to pragmatic and aesthetic criteria like simplicity and non-ad hocness. In conclusion, the intellectual currents flowing from Henri Poincaré in the period surrounding 1893 represent a watershed moment in the understanding of science. He was a uniquely positioned figure, an insider whose mastery of classical physics and mathematics was second to none. From this position of authority, he launched a subtle but devastatingly effective critique, revealing the conventional, definitional character of the very laws that his contemporaries held to be absolute truths. His philosophical insight, forged in the crucible of his work on non-Euclidean geometry and deterministic chaos, provided the intellectual license for the 20th century's revolutions in physics. He demonstrated that the laws of physics are human constructions, magnificent and powerful tools for organizing experience, whose forms are chosen for their utility and elegance. He was a conservative revolutionary, a man who, without raising his voice, quietly redrew the blueprints of scientific knowledge. His legacy is the understanding that the edifice of science is a dynamic structure, one whose foundations are conventions we choose, and whose strength lies in its capacity for profound, self-critical reconstruction. He taught us that the physicist is a creative artist, and the laws of physics are their most sublime and useful creations.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.